So now let's look at how we would examine the relative strengths of acid and bases. So for a strong acid, it's fairly easy. We have HX plus H2O liquid giving a full dissociation, giving us H3O plus X minus. And there are 15 examples of either strong acids or strong bases. Okay, if you look at table 4.1 on page 125 of your textbook, you can see a list of those, which I gave in a previous video, and you need to know those. Everything else is going to be considered weak, and we're going to have an equilibrium established to analyze this acid-base reaction. So here we have our HX plus H2O liquid in equilibrium with H3O plus in aqueous solution plus X minus in aqueous solution. So here this is the acid dissociation constant for our weak acid HX. And we can use some of Le Chatelier's principle to try to determine which way this equilibrium would shift. So if water is a stronger base than X minus, our equilibrium is going to shift to the right. And if the equilibrium shifts to the right, we can say most of the acid, in this case HA, is in the ionized form. Okay, so our equilibrium shifts over to the right. If, on the other hand, A minus is a stronger base than water, then our equilibrium will shift over to the left. And that means most of the acid, or HA, is in the unionized form. Okay? Another thing that we can say from this is that the farther the equilibrium lies to the right, the stronger the acid. And we're going to have more ions present. Okay? So one way to also look at this is we can look at the relative strength of an acid and its conjugate base. So we can kind of get two statements from this. Number one, the stronger the acid, the weaker the conjugate base. Also, the weaker the acid, the stronger the conjugate base. Okay, so it's going to be based on the ability for this equilibrium to shift back and forth. Okay, I'm going to come back up here and we're going to look at this particular expression, and we need some type of equilibrium constant in order to describe the equilibrium here that we have for a weak acid. So for all of our equilibrium constants, we have an equilibrium constant K. The subscript we're going to use to describe acids is a Ka. So for this particular case, our Ka is going to equal the concentration of H3O plus times the concentration of A minus divided by the concentration of HA. And remember, when we write equilibrium constants, we do products divided by reactants, and we don't include species that are pure liquids. Okay, so if we have a strong acid, our equilibrium is going to shift over to the right, and our Ka is going to be large. Okay, because if our Ka is large, that means we have a large concentration of H3O plus and an X minus in solution. Okay, if we have a weak acid, that means our equilibrium is going to lie more to the left. Our Ka is going to be small. And because that Ka is small, the weak acid, we don't have as much concentration of those H3O plus ions in solution, so our acid is going to be weaker. Okay? And from this, we can say that the larger the Ka, the stronger the acid. And likewise, we can make the same claim for bases. The larger the Kb, the stronger the base. And everything here, all this equilibrium would work just the same if we were analyzing bases. So when we're looking at the relative strengths of acids and bases, if we have a strong acid, you typically won't see a Ka written for those because there is full dissociation. There's no equilibrium. The Ka is really, 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 really large. For all of our weak acids and weak bases, you're either going to see a Ka or a Kb. And the larger the Ka, the stronger the acid, and the larger the Kb, the stronger the base. And we can use this to analyze certain problems, which we'll see an example of in the next video.